In this lesson, we're going to be taking a look at a lot of triangles that have this basic setup right here, where specifically we have an angle and we have a hypotenuse of 1 in a right triangle. And we're going to start by just taking a look at this particular one without a lot of numbers involved here. And then we're going to start extending that out and see what kind of patterns emerge out of the whole picture based off of just that. So if I were looking just at this picture here and I wanted to figure out what is the value of x. So I want to know what's the length of side x here. In order to do that, let's say I actually do have our angle here. Notice I could do it in terms of cosine because x here is the adjacent side. The 1, of course, is the hypotenuse. So then to figure out x, I'd say cosine of theta equals the adjacent over the hypotenuse. That would be x over 1. But notice the cool thing about this one, and why I'm particularly using the hypotenuse of 1 today, is that this simplifies down. If cosine of theta equals x over 1, then cosine of theta equals x. Therefore, we know that that actual side length is just the cosine of theta. Now let's also take a look and see what's going on with y over here. Again, I'm starting from angle theta. Y is the opposite side, and of course the 1 is still the hypotenuse. And so that would tell us that we're going to be using sine in order to figure out what side y is. So this would be sine of theta equals the opposite y over the hypotenuse, 1. And again, notice it's y over 1, which we do on purpose using that hypotenuse of 1 because y over 1 is just going to equal y. Therefore, we can know that that side length can be found simply by just doing sine of theta. And so kind of the big theme that we get out of today is saying that when we have a hypotenuse that is just 1 unit long, the other legs can be found just by doing sine and cosine. Now, we're even going to take it a step further here though, because in this particular case, we can also see that we can get coordinates dealing with all this on the regular coordinate plane. So I want to now put on a regular like Cartesian coordinate plane here, where I'm going to put 0, 0 where my angle measure is. So the angle here is going to be at the origin that I'm going from. All right, now if that is the origin, then notice that in order to get the coordinates of this point out here, I'm going over and up by the same leg lengths of my right triangle, which remember I had called x and y. But notice the x and the y here, I also found out that I could figure out x by just doing cosine of theta, and I could figure out y by doing sine of theta. Therefore, for this point, we can see that the x coordinate of that point would have to be cosine of theta, and the y coordinate would have to be sine of theta. This actually ends up being a really important idea as we go forward, as you're going to see. Because remember, this particular triangle that I was looking at, I just labeled the angle as theta. We didn't do it just for one particular angle. We discovered that this would work for any of those angles. And what we're going to be doing is we're going to be looking to see what does this actually look like if we start changing theta and tracing out those coordinates. So I got my basic triangle here. And what I want to do is I want to try moving that theta to a different value. So let's move it up there. Well, notice I still have this was one of my values, so I'm just going to leave those in the gray there. And then I can see that point ends up getting there. Let's take it out another step. So we can see there what's going on. What if I keep going around here? What if I end up bringing this up to here? Where will that be? Well, notice there we can end up getting that same point. The cool thing about this point is we can actually know the exact coordinates of this without having to do a whole lot of work either. Because notice in order to get to this point, we aren't going over at all. So our x coordinate is going to be 0, but we are going up 1. And so you can see that we could actually figure out the coordinates of that point. Similarly, actually, we could actually figure out the coordinates of the point if we just had our angle sitting down there. Because there we're going over 1, and so my x coordinate would be 1, but I'm not going up at all, so that would be a y coordinate of 0. So we can actually figure out the coordinates at that point as well. So we start seeing that we do have a coordinate plane here, And these are going to be coming at some set values. And what I'm particularly interested in at the moment, though, because we are going to come back to those actual numbers involved, is the shape that's getting traced out by those points. You see, we've got some of those drawn in. Let's throw in a few more here. What shape do you see us tracing out here as we move that angle to different values? Well, hopefully, as you take a look at this, you're starting to see that we're going to be ending up getting a nice smooth curve there. In fact, that kind of looks like it would be the corner of a circle. And so we might well see that, yeah, we would kind of expect a circle to be showing up here. But of course, we could verify that by continuing to actually test that out. I could just keep tracing this out, and I can actually calculate the points. I could actually go through and break out a calculator. And remember, we figured out that to find the x-coordinate, we could do cosine of theta. And to figure out the y-coordinate, we are doing sine of theta. I could actually just plug those in for any given angle and be able to figure out what the coordinates of the point are that I'm getting out of it. It's just that in this case, it might be a little bit trickier for you to visualize what's going on and why we could still use cosine and sine, because normally we need to have a right triangle, right? And normally that right triangle is coming down somewhere over here. But notice that's not happening in this case. If I'm going to build my right triangle in this case, it ends up having to go straight down, and so it's actually on the left side this time instead of on the right side. Then if we put theta in there, then we can see theta, remember, was that angle at the origin. So it's the angle here at the center. But all of a sudden, this theta would be a little bit awkward, because let's say this theta here is about 60 degrees. But 60 degrees isn't over here. It isn't over on the left side. If I'm talking about an angle on a circle that's at 60 degrees, that would actually be about 60 degrees from here, so it's actually going to be going up more like that. So I don't want to use 60 degrees for that angle. I need to be able to use something that still is correctly measuring the angle. Remember, we looked at how to measure angles on the circle. We need to go from 0, which is straight over to the right here, and then we go counterclockwise from there. So that's actually where we'll call theta. And all of a sudden, this is where things start looking a little bit different and a little bit weird, because our theta is all of a sudden outside of our triangle. But we still can actually make it work. Remember that my x-coordinate is cosine and my y-coordinate is sine. In this case, remembering that our center here is 0, 0, if I want to then know what are the coordinates of this point up here, notice that in order to get to that x-coordinate, I'm going to the left. And then the y-coordinate, I'm going up, which means that my x-coordinate, I would expect that to be a negative number, and my y-coordinate should be a positive number. That is actually what making our theta here still be measured from 0. That's what that allows us to do, is that's going to actually give us a number where the x-coordinate is negative. If you actually try some numbers doing the sine and cosine values, you'll find that sometimes sine and cosine are positive, but other times they actually are negative. And this is why, because it's actually giving us the coordinates of a point on the standard Cartesian coordinate system. It's not just telling us a length. There's actually been a little bit more to it that we just hadn't looked at before. And so if we continue this idea now and put in some points for a few other possible thetas, like I could go ahead and continue going around there, and really I could just keep going and moving that radius all the way around to get lots of different points, you see that they do indeed all end up falling on that circle, which I hope makes total sense, because really all we did in order to trace out those points is we just took this line and we traced it around. So it was anchored in the center, and then we just moved it around, tracing that outside point. And of course, that would give us a circle if we traced it out, right? It's just that we didn't do it that way. We did it instead by figuring out, okay, what would sine of the number and what would cosine of the number be, and actually looking to see where those points happen to end up. And so therefore, we can see that, yes, if we take the cosine and the sine values and plot them together, we get a circle. And this is actually a very important circle. This is actually called the unit circle because remember we centered it here at 0, 0, and then it had a radius of 1. So remember I was drawing that line around with that radius of 1. And the reason why it's called the unit circle is because the radius is 1 unit long. And then from the work we just did, we saw then that the coordinates of any point on the unit circle can be found by doing cosine, comma, sine. Notice that is an xy coordinate pair, where we're saying that the x coordinate can always be found by doing cosine, and the y coordinate can always be found by doing sine. This information here should go into your notes if you haven't already put it there. And this is going to be kind of a theme of stuff we're taking a look at this week. The big ideas coming out of this particular lesson that I need you to be able to remember are: 1, the definition of a unit circle being the circle that's centered at 0, 0 with the radius of 1. And the other critical learning from this particular lesson is seeing that I can find the coordinates of any point on that unit circle by doing cosine for the x coordinate and sine of the angle for the y coordinate.